Hello, chemistry students. This is question number 2 from your weak acid strong base titration lesson, or other examples that are also there are your weak base strong acid titration, and I'll post another solution on that later. So let's start to answer this question. So A really just resembles an acid equilibrium problem. So it's asking us now for pH before titration has started. Okay, and we have here acetic acid. We have Ka given to us. We have a volume, right? So begin by making an ice table. Okay, so initially we have a concentration of acetic acid at 0.160 moles per liter. We know that we can ignore water here since it is a liquid. Everything else is aqueous. At time 0, we have no concentration of hydronium or acetate ion, acetate being your conjugate base, which will be more relevant later, minus X plus X based on their stoic ratios, and 0.160 minus X, and we get X and X. So hopefully you're used to doing that, getting these expressions at equilibrium. Okay, so now we can plug this into our Ka expression. So reactant, sorry, not reactant, product over reactants. Okay. Right, there's our Ka expression. Now I'm going to scroll down here. Okay, we know that we have 1.8 as our Ka value, 1.8 times 10 to the negative 5. We can plug in expressions here for at equilibrium for hydronium and acetate. Now this is all over 0.160 minus X. Now we can say hundreds rule, we can say that. So since hundreds rule or 5% rule, hundreds rule applies. Therefore, we can take X and we can cross that out. So we're going to do that here. Okay, so let's simplify this then. X squared over 0.160 is 1.8 times 10 to the negative 5. Okay, I'm going to skip a couple steps here. You cross multiply square root each side, and we end up with X is equal to 1.697 times 10 to the negative 3. Now, remember what that X stands for. It stands here for, well, I was going to write a concentration, but look, it stands for essentially the concentration of equilibrium at equilibrium of hydronium. So, which is equal to the concentration of hydronium. Now the question is asking for what is the pH at this point, so we can say pH is the negative log of this concentration of hydronium, which is 1.697 times 10 to the negative 7. Okay, plug that in and you get a pH of 2.769, and that is pH of your first point, 2.769. Right, haven't rounded to sig figs, but there is the answer for your first point. So on to the second step of this titration, where we're asked to calculate the pH. After we've started titration, but before equivalence, so we've added 8 milliliters of sodium hydroxide. Okay, and again, that's a concentration given to us right here. Now, before we begin, and you could have done this step a bit sooner, but this is the background step, I like to call it. You need to figure out how many moles of acid you have. Right, we have volume, 20 mils, and we have concentration. So it's V times C, volume times concentration, and we convert 20 to 2. convert 20 milliliters into liters, multiply that by the concentration, right? And we end up with 3.2 times 10 to the minus 3 moles. Okay, so this tells us that we have this many moles of acid in total of HA. Okay, remember as just a reminder that as you progress with titration, it reacts quantitatively with the base reacts quantitatively with your acid. It pushes the reaction forward, pushes the dissociation forward. Um, More on that as we get to our equivalence point, the third point. Okay, also remember that once we figured out how much acid is left over after this initial neutralization by these 8 mils of sodium hydroxide, the question then becomes more of a question on the equilibrium of what is left of the acid that is left, right? Because we haven't completely at this point neutralized our acid. So that means that we will have this to consider at the end. Okay, so in other words, this is being left after the 8 mils of base have neutralized, right? This will dissociate like that. We can write a Ka expression, figure out what our concentration is. More on that, but let's start the question itself. All right, so this is the background calculation we will actually refer to for the third pH, for the third point in our titration curve. Okay, sorry, one more thing that we have to do. Remember, at this point, we have a new volume. So we have added a volume of acid and a volume of base, which is 20 mils, or let's just convert that to liters, 20 mils plus, or 0.02 liters plus 0.008, right, for the 8 milliliters. That gives us 0.028 liters as our new total volume. Okay, this is important to consider because we're going to be adding one volume to the next, and it'll change our concentration. So just a couple background things to do. This will continue to use moving forward. This you're going to use right now. Okay, a lot for background stuff, right? Now the first step in solving for the pH at the second point of titration is a stoichiometry step. Okay, so your stoichiometry step is to figure out how much acid remains after neutralization, so after the 8 mils of base. Okay, our second stage is more of an equilibrium problem. Okay, it's more of an equilibrium problem or step because once we have how much HA is left and consequently conjugate base is left, it becomes more of an equilibrium problem that takes this equation, this reaction into consideration. Okay, so that is with a new concentration of HA and related ion. Okay, so let's give us some more room to start our first step. So let's figure out how much base was added. So we have to figure out how much sodium hydroxide is added. We have a volume of 8 milliliters, or that is the conversion to liters, right? And then 0.2 moles per liter is a concentration given to you in the question, and we get 0.0016 moles. Liters cancels out. Now, this part I'd like to call fake ice table because it really isn't your equilibrium ice tables as you're used to seeing. It's more figuring out how much acid has been consumed by base, and you're just using that table just for organization purposes. Okay, so here it is. Let's start to write that down. So HC2H3O2. We know that this reacts with hydroxide. Okay, now a little side thing to mention here, sodium hydroxide, right? We know that will dissociate in a 1-to-1 ratio. So we have figured out here how many moles of sodium hydroxide there is. Okay, that means in a 1-to-1 ratio, we have the same number of moles of hydroxide ions. So since this is the case, therefore we can say the number of moles of hydroxide is equal to the same thing because it's 1-to-1. Notice I've ignored sodium. This is a neutral ion. It has no bearing on the question, so I'm ignoring it. Okay, let's continue with our fake ice table here. Okay. So I was about to write H3O. Okay, but this is our neutralization. So H2O plus C2H3O2. Okay, so ICE. So we know the number of moles. So the reason I call this our fake ice table, because it really isn't the ice table you're used to. We're used to seeing concentration in ice tables. A student a few years ago called it a nice table. Nice table because that n would stand for the number of moles. We're actually using moles here to figure out what our value is. Not really at equilibrium, it's not really at equilibrium, but just how much we have left. Okay, so we have, to begin with, we have 3.2 times 10 to the minus 3 moles of acid. See where that background calculation came in? Right? 3.2 times 10 to the minus 3. That's important to put over there. Now, we also, before this reacts, we also have figured out that we have, I'm going to convert this to scientific notation, 1.6 times 10 to the minus 3, right? And we can say just before they neutralize each other, we're going to have nothing left. In fact, this is a liquid, so we can ignore this. We're going to have, well, although, we're not talking about concentration, so that isn't entirely accurate. I'm thinking as I go along here, but because this isn't a real ice table, we could write well, 0 for this, really, because it's just moles. Okay, so at this point, we have nothing made before this has neutralized. So we know that this is going to consume, is going to consume itself in the neutralization. By this I mean our base hydroxide is going to consume itself in the neutralization completely by neutralizing the acid. This isn't a negative here, it's just a dot. Not on purpose either. Okay, so minus 1.6 times 10 to the minus 3. Okay, then our products are plus. Okay, I'm going to leave this because this isn't really relevant, right? Know that it isn't a real ice table, and it does actually, moles of water do actually exist, but I'm just going to leave that. And we have positive 1.6 times 10 to the minus 3. So what we have here then is minus 1.6 times 10 to the negative 13. So I plus C will give us 3.2 times 10 to the minus 3 plus negative 1.6 times 10 to the minus 3. It's really subtraction. So what we're left with at this final stage is this many moles of acid, 0 moles because this gets consumed completely by the neutralization reaction, and then also 1.6 times 10 to the minus 3 of conjugate base, or of acetate ions. Okay, so we have moles, right? These are all moles. Okay, but we have a new volume. Recall that new volume, that background calculation I said that we would need to pay attention to in this stage. Okay, we have 28 mils. So new concentrations. New concentrations. That now is important to figure out, not a 2. Okay, so 1.6, we know the number of moles of acetic acid. We have also our new volume. Okay, and we end up with 0.05714, and that's molarity, moles per liter. Moving on to our acetate. Turns out we have the same number of moles. Okay, which means we have the same concentration. 1, 4, begin. Okay, this is our first step, Now our second step, our stoichiometry step is now done. We have the concentrations required. Now our second step is our equilibrium component of this. So we have a Ka value, right? It's given to you in the question, 1.8 times 10 to the minus 5. Okay, and that expression looks like this. Right? I'm going to refer back briefly to here, right? We're going to get write our expression from the dissociation of our acid, our remaining acetic acid. So products over reactants. Okay, acid. Okay, good. So, okay, acetate ion, we know that concentration right there. Acetic acid, we know that concentration is right here. Plug those values in, and essentially they're the same, so they're going to cancel out, but let's just go ahead and do that. 5, 7, 1, 4. And we're going to figure out what that should be concentration, what our concentration of hydrogen ions is, but let's just substitute everything inside. Times 10 to the minus 5. All right, so these cancel out completely. I'm going to continue up here. And what you can end up with essentially is that the concentration of your hydrogen ion is 1.8 times 10 to the negative 5. 1.8 times 10 to the negative 5, and you're almost done. Lots of blue here. Let me choose a different color for our pH so that we look at that as a different step. Okay, so pH we know is the negative log of the concentration of your hydrogen ions, or hydronium, of course. So negative log, we now have this concentration. See, it's right here. Plug that value in, 1.8 times 10 to the negative 5, and we get 4.74. That is our pH for the second point. Right, so in this point now, you're trying to figure out what your pH is at equivalence, but notice, unlike our lesson example, it doesn't give you volume. So you have to think about what we need to do to figure out that volume. So here, volume at equivalence is not given. Okay, so this means we need to figure out how many moles, rather, what volume in milliliters or liters of base is needed to titrate. Now, remember our background calculation that I said we were going to refer back to. We know the number of moles of acid, right? It's 3.2 times 10 to the minus 3 moles of acid. And we know that it reacts, that our base is going to react quantitatively, pushing this acetic acid to complete dissociation, right, despite it being a weak acid. So that means that we'll need an equal number, or the same, moles of base. Okay, so let's start working on that. So since we need this many moles, so 3.2 times 10 to the minus 3. And before I move on, just a brief reminder. Now, these can be equal. These have to be equal, and we can make the conclusion that therefore we need the same number of moles of sodium hydroxide, because everything's a 1-to-1 ratio here. Acetic acid dissociates in a 1-to-1 ratio. So we have these many moles of acetic acid. We therefore know that at equivalence, we're going to have the same number of moles of hydrogen ions, right? And because NaOH dissociates in a 1-to-1 ratio also, we therefore know that we need the same number of OH ions. Now, if that were not the case, right, then this calculation would involve another step or two. Okay, but let's continue. So we need that many moles of sodium hydroxide, really of hydroxide. Okay, so what is our volume? We know that volume, right, from C, right? We know that volume is moles divided by concentration. We know moles, 3.2 times 10 to the minus 3. Okay, concentration of base given to us in the question is 0.2 moles per liter. Mole cancels out, and you're left with a volume of 0.016 liters. Okay, so that's the volume you need of base. So let's just say, therefore, equivalence occurs at 16 mils of sodium hydroxide. Okay, now think about what ions are present here. Just as a reminder, all our acid is gone, right? So we have no acid left, right? We do have sodium hydroxide, or so rather sodium floating around from the dissociation of sodium and hydroxide, but that's irrelevant. It's a neutral ion. We used, right, 16 mils of base, but this is completely neutralized, so we have no more hydroxide left. So the ions that are really present here is just that conjugate base. It's just your acetate. So ions that are present, that is present here, because there's just one, is our acetate. And this exists, don't forget, this exists in water. Okay. Let's continue. Right, so acetate, being the conjugate base of a weak acid, will behave like a base. Again, it is a conjugate base of a weak acid, so it behaves like a base. In the presence of water, it will look like this. Right? We can then get a Kb expression from this. Right? Kb, because it is, again, behaving like a base according to the Bronsted-Lowry definition. Okay, but the problem right now is we don't know what our Kb value is. But what we do know is that there is a relationship between Kw, Ka, and Kb. Right? We know what Ka is, we know our Kw constant, so we can figure out Kb. Right? That's just Kw divided by Ka. That's 1 times 10 to the negative 14 divided by our Ka value given to you in the question. And we get a Kb value of 5.6 times 10 to the negative 10, right? Quite low. Okay, the other calculation we have to consider, the other change that's happening here is that there is a new volume. Right, so our volume total is now 16 mils of base plus 20 mils of acid. And that equals 36 milliliters, or 0.036 liters. So that means our concentrations have changed, right? So concentration, we need to figure out what is the concentration of our acetate ion. We know the number of moles, right? Back up here, we know the number of moles of our acetate ion. I know I'm circling, I'm putting a box around acid, but remember this acid associates in a 1-to-1 ratio. So yes, we have the same number of moles of hydrogen ions, but because it dissociates again in a 1-to-1 ratio, we have the same number of moles of acetate. So here we go, 3.2 times 10 to the negative 3. This is moles. We're going to divide that by the new volume. Okay, and we have that concentration then of acetate ion. All right. So now what we can do is we can write an ice table. Okay, so this is our equilibrium problem now. Since we have no acid left, so we don't have to worry about Ka anymore. We do need to consider, though, Kb and our Kb expression. That, of course, comes from our acetate behaving like a base, right? Here is our ice table. We know that we have a certain concentration that exists once neutralization has completed. Right, this is a liquid, so we can cancel out. Everything else is aqueous. Time 0, it's 0 and 0. We know that this is a minus x, this is a positive x, positive x. Add I and C, and we get expressions at equilibrium for each of these species. We know our Kb expression. I'm not going to rewrite that. I'm just going to plug it in. Right, Kb is x, these two over this. Okay, now don't forget, I'm going to write the hundreds rule.
Hundreds rule applies. So we can get rid of this x. You do need to say that this applies. You don't have to prove it. Okay, I'm going to simplify everything and fill in that Kb value. Right, that was 5.6 times 10 to the negative 10.
And cross multiply, square root each side, and we get an x value that is 7.019 times 10 to the negative 6. Remember, this means the concentration from our ice table, which really means a concentration of your hydroxide ion. Okay, now, because we have the concentration of our hydroxide ion, POH can be easily determined as negative log of 7.019 times 10 to the minus 6. Okay, and that is equal to 5.15. pH is then 14 minus POH, which is 14 minus 5.15. Just realize it doesn't really look like a 5.15, but it is. Okay, and we get a pH of 8.85. Okay, and that is our final answer for this third point in our titration. The final point in titration, our fourth point, is beyond equivalence. So it says, what is a pH after 20 mils of sodium hydroxide? It doesn't say beyond equivalence, but we can assume that based on how this question is set up. This is our fourth point. So what we need to then figure out is how many mils, or remember, I should say, that we have a certain volume of base that was required. Remember, that's 16 milliliters, certain base required to reach your equivalence, right? That means after titration, right, at this point, after titration and beyond your equivalence, you have a new volume. According to this, it's 20 plus, well, we have 20 mils of base. We had 20 mils of acid for a total of 40 mils, right, or 0.04 liters. Now, we've gone over, so we are 4 milliliters beyond our equivalence point, right? Because we have added 20. We only needed 16. So we are 4 milliliters beyond that. Okay, so now a bit of a since and therefore statement for some logic here. So the only there should be square brackets. The only significant source of concentration of hydroxide ions is from the extra titrant. Okay, that means we only have to worry about the 4 mils of extra hydroxide added. Okay, So how many moles then? How many moles of hydroxide have we added from 4 mils? We have 0.004 liters, just converted that to liters, times 0.2, which is the concentration given to you in the question, and you end up with 8 times 10 to the negative 4 moles. So you have that many moles of hydroxide present. Remember, though, that you have a new concentration. A new volume, which gives you a new concentration. We know that concentration is moles divided by volume. We have figured that we have 8 times 10 to the negative 4 moles of hydroxide with a new volume of 0.04 liters. Right, we divide these two for the new concentration and we get 0.02 moles per liter. Okay, this is the concentration of hydroxide. So now that we have that, right, concentration of hydroxide, we can figure out pOH, right, as the negative log of 0.02, that's 1.7. We can figure out pH since it's 14 minus pOH, which is 1.7. And our final pH, final point of this titration is then, we'll end then with a pH of 12.3. That's it. So now you have all 4 points before titration has started, after it started, but before equivalence, your third point is at equivalence, and finally beyond equivalence in this case with 4 extra milliliters of titrant of base. Hope that helps.